This is Shanta, a school student with an artistic bent of mind. She also loves connecting art with mathematics. Today she's going to try her hand at making the fascinating Mobius strip. Let's see how it works. Shanta starts off with a loop of paper. Now, instead of just gluing the ends together, she's going to twist the loop once before gluing. So we get a strip like this, which we call a Mobius strip. Still haven't understood the excitement? Then take a pen and draw a line along the center. You will find that you have drawn a line on both sides of the loop, but without lifting your pen or crossing any edge. The paper has only one side. Now take a highlighter and color the edge of the strip. You'll find both edges are colored. There's only one edge. What we have here is a one-sided surface. The famous Dutch artist M.C. Escher, who Shanta loves, immortalized this idea by visualizing an ant crawling over the strip. Now this ant would be able to walk over both sides of the strip before returning to the start. Welcome to the Maths Factor. In this episode, we're exploring a host of magical shapes like the Mobius strip. We'll meet up with potters, ironsmiths, paper folders and knot tiers throughout the journey through the discipline known as topology. Keep watching, it's going to be quite a ride. Back to Shanta and our Mobius strip, and some more fun stuff we can do with it. If we cut through the line we drew in the center, what will happen? On a normal strip, we would get two rings. But in the Mobius strip, you will end up with a large single loop. Quite cool, eh? Next, Shanta cuts along a line which divides the strip into 1/3 instead of half. What do you think will happen? This time, two connected loops form. There's one half twist in the smaller loop and two half twists in the larger loop. Shanta is pleased with this. Shanta is going to try one more variation. She creates a new Mobius strip, but instead of one twist, she will twist it 2 times, like this. Now what happens when we cut through the middle of this loop? Ta-da! It's 2 rings that are linked together. What fun! Now Shanta could clearly keep continuing along the same lines. But I think we'll take a break from this and figure out who Mobius was. Augustus Ferdinand Mobius was a German mathematician and astronomer. He discovered the Mobius strip in 1858. Curiously enough, the same strip was discovered earlier in the same year by another German mathematician, Johann Benedict Listing, who unfortunately didn't publish in time. If he had, we may just have called it the Listing strip instead of the Mobius strip. In 1882, a mathematician called Felix Klein took the idea of the Mobius strip one step further. To do that, let's look at a bangle first. If we expand it like this, it forms a sphere. Klein, however, took 2 Mobius strips. He then sewed them together like this to create a bottle with a single surface and no boundaries. This shape came to be known as the Klein bottle. Now, what makes this both baffling and fascinating is the fact that it cannot exist in 3 dimensions. Because what is happening here is that the cylinder is actually passing through itself, but without a hole, which cannot happen in reality. But strangely enough, it is mathematically legal. Let's bring in an ant to help understand this. If it walks along the sphere, it can circumnavigate it, but go inside it, it'll need to make a hole. On the other hand, an enterprising ant could walk all over the Klein bottle, up, over, in, through, round, inside, round, out, round and up to where it began without crossing any edge. Now, all these odd shapes are part of an area of mathematics called topology. Topology is a modern version of geometry which studies different shapes and sizes. Let's try and see what makes topology different from geometry. Take any 2 shapes, say 2 triangles. We cannot stretch them or bend them, but we can move them and flip them over. When placed on top of each other, they look identical, or in geometrical terms, congruent. Shapes like this fall within the space of classical or Euclidean geometry. Next, we're going to study perspective. First, take a look at this plate. From directly above, it looks round like a circle. But walk away a few feet and look at it, and it looks much wider than long, like an ellipse, because of the angle you're at, which is the way it has been drawn. This is called perspective. While drawing, 2 things are considered the same if they're both views of the same object. Now we move to the home of Ravikant, the potter, to see how topology works. Topology basically investigates those properties of shapes which do not change under continuous bending and stretching. Ravikant first takes clay off the wheel and builds a sphere. He then molds this to form a cube. He then molds the cube again to make a figure doll. In topology, all these 3 shapes are the same, since you can obtain one from the other without cutting or punching a hole. Now, holes are very important in topology. So if we use our clay to form a vara-like shape, let's see what it can transform to topologically. Our vara has 1 hole, so all our shapes need to have 1 hole. So an enterprising potter can mold the vara to form a needle-like shape and then eventually a coffee cup. Here the hole is the handle. In fact, the idea of a vara or a donut and coffee cup being the same is a classic idea in topology. Now all these figures are the same topologically speaking. However, a figure of 8 is not because it has 2 holes, not 1. On our journey through the magic of topology, we've explored a bunch of interesting shapes. Our next shape takes us to northern Italy, to the Lake Maggiore. Now in the middle of the lake are 3 islands, Isola Bella, Isola Madre and Isola Superiore. These islands belong to the Borromeo family. They own a lovely Baroque palazzo. But what interests us here is their family logo, which is 3 interlinked circles. Now the curious fact here is that all look interlinked. But if we cover the red circle, the other two look they're on the top of the other, not linked in any way. We can do the same thing again by covering the green and blue circles also. Now the idea is that if you cut one ring, you will free the other two. Let's try our hand and constructing Borromean rings to see if that really works. To do that, we need to meet up with Om Prakash, who is an ironsmith. What he does is take two pieces of iron. He then molds them to form rings. He places one on top of another. Then he creates a third ring that he weaves through the other two. Under the first, over the second, and back under like this. He welds this one together, and we have Borromean rings. Now what happens if he cuts one ring? All three fall apart. Now Borromean rings seem to have a mystical resonance. If we travel to the Marundeswara temple in Chennai, we can see Borromean figures carved in its pillars that date back to the 6th century. In Christian art, Borromean rings are often used to represent the Holy Trinity. The same arrangement can be made with interlocked triangles. These were a symbol of the warring Vikings and is known as the walk-knot. Now the walk-knot symbol is often found in places where there are fallen Viking heroes. It has also been found carved into a bedpost used in a ship burial. Now let's head back to Shanta's workroom. She is still engrossed with paper and is trying to replicate another fascinating shape. Let's look at this paper. It has two sides. If we look at 3D objects, a pyramid has 4 sides, a cube has 6. Now it's pretty rare to see a 3D object with 3 sides. Shanta is trying to make one. It's called a hexaflexagon. She starts off with long strips of paper like this. And then she starts folding them in a zigzag way to make shapes. Now let's slow Shanta down a bit and see what she's doing with this paper. She folds them to form a series of equilateral triangles. Then she does a series of flip overs. She glues it together to make our hexaflexagon. Now she draws smiley faces on one side and sad faces on the other. She then folds the hexagon along the lines to loosen it up. She flips it over and we have another side. No smiley or sad faces. Where did that come from? Shanta has made an object with 3 sides. Now Shanta is going to make an even more interesting hexaflexagon, which will have 6 sides. Let's see if that's true. We color one side red and then keep flexing. And as 3 new sides appear, we keep coloring them. Blue first, then green, yellow, pink, and purple. Wow! One paper with 6 sides. Quite magical, right? Many years ago, in 1939 to be precise, an Englishman by the name of Arthur H. Stone who was studying at Princeton, created the shapes that Shanta just made. We're exploring an area of mathematics called topology. In this episode, we've already explored holes, rings and strips. Now let's move to knots. Knots populate a life. From tying a shoelace to tying a bow, to untying an animal, to tying a ribbon on a present, knots are an integral part of our lives. And they've been for a very long time. Before we start off on knot theory, Dave is going to help us figure what a mathematical knot is. For this, he pulls out a rope and tape. He first ties a knot in the rope. He then tapes the two loose ends of the string together. He has now trapped the knot on the string. No matter how long you attempt to disentangle the string, you will never succeed without cutting the string open. Now this models the mathematical concept of a knot. Now Dave is going to show you how two knots are equivalent. Here's one knot. Now Dave changes the knot, which means he rearranges it without cutting the rope to look like this. According to knot theory, this and this are equivalent. Now we have a bunch of kids who are going to try another fun game to learn about knots. Let's call it Untwister. They all stand in a circle, then they join hands, but not with the person standing next to them. And both hands are not joined with the same person. They then twist and climb and duck under each other's arms, but don't let go of each other's hands, until they're standing in a circle again, completely untangled. If you have enough people, it sometimes happens that you end up in two circles. So a fun game can teach us a bit about maths. Now the mathematical theory of knots was born out of attempts to model the atom. Near the end of the 19th century, Lord Kelvin suggested that different atoms were actually different knots tied in ether that was believed to permeate all of space. Physicists and mathematicians set to work making a table of distinct knots, believing they were making a table of the elements. Now this idea, fascinating though it was proved untrue, but it led to the development of knot theory as a mathematical discipline. Let's move to Loveleen Bhagat, who's an artist. She's going to try her hand at drawing some knots. It's rather fun. So what she does at first is draw a random squiggle. Now using this squiggle as a guideline, she makes under and over pattern. And then she completes the knot. Then she tries her hand at a more elaborate squiggle. And with a felt pen this time, it can have as many loops as possible. But the final two ends. One interesting insight: any direction that you go and any amount of branchings that you take always make a perfect over-under pattern. Now Mrs. Bhagat gets more adventurous and tries her hand at drawing Celtic knots. These are historic patterns that appear in Scotland and also in Roman mosaics, and patterns by Vikings and Saxons as well. Columns, which are traditional patterns drawn outside homes in South India, are also knot-like. Mrs. Bhagat tries her hand at a traditional Naga mandala drawing. The Naga mandala is a pattern formed by a snake which weaves itself into a number of knots called Nagabandha. Snakes are considered auspicious, and one can find these Naga mandalas drawn on floors or carved in the wall, pillars of temples in many parts of India. I think we are all knotted out, So let's move into another zone where I want to introduce you to my favorite mathematical theorem. It's called the hairy ball theorem, and yes, it's a name that charms me. So what does the theorem state? Take a ball covered with hair all over. Now, however we comb this ball, the hair will never lie flat. There will be at least one special point from where all the hairs radiate, or a tuft where all the hairs meet and protrude. Well, it can be applied to other situations such as wind currents on planet Earth. At each point on the Earth's surface, we can measure the wind speed and direction, which is equivalent to the length and the direction of a hair. Now, the closer the points, the closer the wind velocities. Using this theorem, we can conclude that if the wind is blowing in some direction at every point on the Earth's surface, then there must be at least one point where the wind speed is 0. That is, the wind is not blowing and it is calm. This is equivalent to the hole in the hair. This point is the eye of a cyclone or anticyclone. Like the swirled hairs on the tennis ball, the wind will spiral around this 0 wind point. So the theorem tells us that given at least some wind on Earth, there must at all times be a cyclone somewhere. Well, this is more theoretical than literal, so don't go chasing the cyclone just yet. We've found mathematics in some of the most unexpected corners of our lives. We've explored a bunch of fascinating shapes like the Mobius strip, the Klein bottle, or the Borromean rings. We have checked out knots in paper with more than 2 sides. We could keep going, but let's save some stuff for another episode. Keep watching the Maths Factor for more fascinating and interactive mathematics.